So this video is about optimization problems, specifically optimization problems that arise in machine learning. A lot of machine learning or AI can be posed as optimization problems. So far, for instance, we've considered least squares regression, L1 regression, very briefly, logistic regression. Each of these problems involved minimizing some function, right? We minimize the mean squared error in least squared regression, which is equivalent to minimizing the L2 norm. In L1 regression, we minimize the L1 norm, which is the absolute value of the error summed. In logistic regression, we minimized what's called the logistic loss function, etc. So all of these are examples of what are called loss functions. All these functions are what are called loss functions, which are functions that quantify how badly a model explains the data, right? And the goal in these problems, at least, is to minimize this badness, right? So we want to minimize these loss functions, minimize the mean squared error, minimize the L1 norm of the error, minimize the logistic loss function, etc. So as we've seen before, supervised learning has the following format. We have some data. The data contains some inputs. The inputs go into some model with some unknowns, B0, B1, B2, etc. And based on the inputs, the model is able to predict some outputs. Let's call this Y model. We can compare this Y model with Y data, and this comparison is achieved by this loss function. And what's output is the badness of the model, or the loss, some measure of the error. And we want to minimize this. We want to find B0, B1, B2 such that this is as small as possible. That's kind of the goal. Okay. So that's an optimization problem, and so we now look at optimization problems. Of course, optimization problems don't just arise in machine learning. They're useful in all of science and engineering, and we will sort of very briefly look at optimization problems from the perspective of using them in machine learning, but also we will see some applications in other aspects of science and engineering as we go along. Okay. In science and engineering, of course, we want to say pick parameters in a design to minimize or maximize the performance or life of a machine, minimize cost, etc. Okay. Just some terminology here. The function that we want to optimize is usually called the objective function. Okay, so that's the thing that you want to minimize, your objective. I've so far talked about minimization and briefly maximization, maximizing performance or life of a machine. Minimization and maximization are equivalent problems. Maximizing a function f of p is the same as minimizing the function minus f of p. That is, we will get the same p-value. They should say the same p-value of p for either of these optimization problems. Maximizing f of p and minimizing minus f of p will give us the same value for p. So because of this, it is sufficient to study just minimization problems. Most software that exist minimize by default. Some of them may have an explicit flag that you can set to ask it to maximize a function, but many softwares don't have such a flag, and you just really have to define your objective function with a negative sign so that it does the appropriate thing. Okay, so let's for this video just look at sort of high-level ideas and terminology related to optimization. And a good place to start is the optimization. So where we are trying to minimize f of p, where f itself is a real number, f of p is a real number, and p is also a real number, right? P is one-dimensional, is a one-dimensional real number. F is a function of one scalar variable p. Sometimes people might write this as f colon r to r. In other words, the input is r, the output is r. The input is a real number, the output is a real number. I do want, this is a sort of minor technical remark. When we say P belongs to R, where R is a set of real numbers, this usually means that P can take any real valued number, and it turns out by convention we do not include plus minus infinity as a real number, because that they're not necessarily numbers. They are limits, but not necessarily real numbers. Okay, so that's what we mean by P belongs to R. Any real number, but not necessarily plus minus infinity. Okay, we want to minimize a function f of P. What are the conditions? How do we find the optimum? We usually find the optimum, as I'm sure all of you know, by looking at what are called necessary conditions for optimality. A point P star is a local minimum only if the slope at point P is equal to 0. The slope at point P is you take the derivative of f with respect to P, evaluate it at P star, and if that's equal to 0, then that point could be a minimum, right? Or more precisely, what do we mean by necessary condition? What we mean by that is, if you have a minimum, then that minimum will satisfy this condition. Okay, so if you have a function like this and you have a minimum, the minimum will have 0 slope. Okay, that's what we mean by necessary conditions. Sufficient condition for a minimum is P star is a minimum if you have the slope equal to 0 and the second derivative evaluated at P star is greater than 0, right? So why do we care about that? Again, this is familiar to all of you. Slope equal to 0, df by dp equal to 0 can mean a minimum, right? So at this point the slope is equal to 0. Maximum, at this point the slope equals 0. An inflection point, at this point the slope is equal to 0, or it could just be completely flat, right? So all of these possibilities are accommodated by slope equals 0. So to actually be able to distinguish between each of these possibilities, we look at the second derivative, and if the second derivative is greater than 0, then it's a minimum, because what is the second derivative? The second derivative is the rate of change of slope. The slope on this side is negative, the slope on this side is positive, the slope here is 0. You go from negative to 0 to positive slopes, so the slope is increasing as P is increasing, which correspond to second derivative greater than 0, right? All this condition means is that the slope is increasing when the slope is 0. Okay. Okay, so that's it for sufficient condition for optimality. What does sufficient condition mean? If these two conditions are satisfied, then P star is a minimum, right? P star is a minimum if. Necessary conditions means only if. We'll talk about that in slightly greater detail here. I just wanted to briefly remark there is also the possibility that if the second derivative is less than 0, if it's less than 0, it's a maximum. If it's equal to 0, it could be an inflection point, it could be completely flat, it could actually also be a minimum. Okay, it could also be a minimum if the second derivative is completely equal to 0. I should think about that. Think of an example where the second derivative is equal to 0 and it's actually a minimum. Okay. I've used the word necessary conditions and sufficient conditions here, and I've boxed these terms only if and if in red. So I just wanted to briefly talk about this math terminology here, because maybe this is something that would be useful if you read some mathy books on this or any other topic. You may be familiar with these things. Okay, so a statement A is a necessary condition for a statement B. So in other words, for B to be true, to say that A is a necessary condition for B is the same as saying B is true only if A is true. Okay. which is exactly the same as saying B implies A, right? So that saying that A is a necessary condition for B means that if B is true, then A has to be true necessarily. That's why it's called a necessary condition. Okay, these three statements are equivalent. And then if we say a statement C is a sufficient condition for a statement D, that statement as a whole is equivalent to saying D is true if C is true. Not only if, but if. So if C is true, D is true. That's what we mean here, equivalently. Or another way of saying that is C implies D. Okay, that's what we mean by a sufficient condition. These three things are equivalent statements. Then finally, you might have heard of the notion of a necessary and sufficient condition. So E is a necessary and sufficient condition for F. That statement is equivalent to saying F is true if and only if E is true. Completely the same as E is true if and only if F is true, which is equivalent to saying E implies in both directions F. So F implies E, E implies F. So you can write that like this, or write it in two different pieces. These are all equivalent statements. This statement, this statement, this statement, this statement, and these two statements are all equivalent. Okay, this is just a math aside. Okay, so where are we? We just wrote down the necessary condition and the sufficient conditions for minimization of a one-dimensional function. Okay. Let's briefly talk about what assumptions we've implicitly made. I didn't try to very precisely write down the assumptions so far, just because you're mostly familiar with these topics. But implicitly, we've made the assumption that the function f is twice continuously differentiable, right? What does continuously differentiable mean? It means that it's differentiable. Twice continuously differentiable means it's differentiable twice, and the second derivative and the first derivative are continuous, and the function itself is continuous, of course. That goes without saying. So functions that have these properties are called C2 functions. If the function is arbitrarily differentiable continuously, then those functions are called C infinity functions. C1 function would be once continuously differentiable, which means that you have a derivative, and the derivative is continuous everywhere. Okay, so why are these assumptions important? Well, of course, these conditions rely on having derivatives, right? So those are based on derivatives. If the derivatives are not continuous, for instance, if the first derivative is discontinuous, like so, well, that means that, well, at this point, the derivative is not even defined. The right and the left limits of the derivative are defined, but the derivative itself was not defined at that point. And then the minimum is at this point where the function is not differentiable. It's a kink in the function, right? Okay, so I'll just leave it at that. So far we've assumed differentiability, which is a reasonable assumption in many situations, but not necessarily all situations. The other assumption that we've made, kind of, is that we've kind of implicitly ruled out or not considered p plus minus infinity, right? So these conditions about the slope being 0 and the second derivative being positive essentially rely on, or not necessarily rely on, but are most useful or relevant when p is not going to plus or minus infinity, because when at infinity you can actually have sort of a minimum without the slope being equal to 0. So imagine a function that sort of goes down, 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 keeps going down as p goes to infinity, and the slope never goes to 0, right? So you can even imagine a linear function that just keeps decreasing as p goes to infinity, and you might reasonably say the function achieves its minimum. Of course, never achieves it, but as p goes to infinity, the function goes to its minimum possible value, which is in this case negative infinity, right? In such cases, we might say if p goes to infinity or minus infinity, we might say the minimum goes to infinity, or the minimum is unbounded, or informally we might say p is at the optimum is at infinity. If f, the function value itself, takes values plus or minus infinity, we might say the function is unbounded above or below, depending on whether it goes to infinity or minus infinity. Okay. So that's about infinities. We don't have to satisfy this condition. Another little sort of caveat is that the range of values that your parameter p might assume might be bounded. Depending on the situation, you might say p just is allowed values between a and b, including a and b, and again the conditions that the slope need to be 0, this condition that the slope needs to be 0 is no longer necessary when you have these bounds. So imagine this function in this range. So let's say this is a, this is b. In this range, the function does not have slope equal to 0 anywhere, but this would be considered a minimum, right? P equal to b. So this is a, this is b, just to be clear. The page appears to have been cut off, I guess. This is a, this is b. This thing should go up there. And p equals b, this point is the local minimum, because if you take any other point p but in this range, the function is necessarily higher than its value at p equals b. So p equals b might be called the boundary minimum because it's at the boundary of your feasible set. So if you have a function like this, and these are the boundaries, this would be an interior minimum, this would be a boundary minimum, right? Just wanted to briefly mention the terminology here, which actually I just used. The notion of a feasible set. For these problems, the feasible set is between a and b, a and b. In general, in maybe even higher dimensions, the feasible set is a set of all x values or p values that satisfy the constraint of the problem. So if you say x is between 1 and 2, then that's a feasible set. If you have x1 and x2 and their values are bounded between in this region, then that's a feasible set, and so on. Whatever values of your unknown parameters that satisfy all the constraints of the problem are called the feasible sets. Okay. Here I really mean p, the same p we've been using before. I seem to have just switched it to x here briefly, but p should be fine. Okay. Okay, so that's it for this video. We'll continue the story in the next video.